let me go over what we were doing last time briefly, and then we'll start for today's lecture. So last time we were taking a look at how to do these kinds of integrations, and we said that for Q4 elements and for higher order elements and in general, we'll use numerical integration to do these types of element integrals. Um, and we saw that a couple of types of numerical integrations last time in one dimension, the trapezoidal rule, the Simpson's rule, and we also saw that the Gauss quadrature is the one that allows you to integrate a polynomial of a certain degree exactly. So if I use n-point Gauss quadrature, how many degrees of polynomial, up to what degree of polynomial can I integrate exactly? Sorry? N is the number of points. So what is the order of the polynomial that I can integrate up to exactly? Right. So it's 2 times n minus 1, meaning if I use one Gauss point, I can integrate only linear functions. We saw that last time, right? Right here. So if I use one Gauss point, we can integrate linear functions exactly. If I use two Gauss points, I can integrate cubic functions exactly, not approximately, exactly. Similarly, for three Gauss points, it would be 2 times 3 minus 1, 5. Quintic order polynomial would be integrated exactly. So that's why people use this Gauss quadrature more often than your regular trapezoidal rule or the Simpson's rule. So we were saying that we will use the same type of approximation in 2 dimensions. What we'll do is we'll map whatever small element of area back to the parent element, and then use one cross or a one-dimensional Gauss quadrature in Xi and one-dimensional Gauss quadrature in eta, and you will have your element integrals. So the same thing we also said for the boundary integrals. We said if you want to integrate whatever quantity that you have over the length, then you should be able to convert that to a Gauss quadrature in one dimension along the edge. And therefore, we also saw that this is related to the area transformation formula in 3 dimensions. And finally, once we have done all your Gauss quadrature, we said that k element, which is defined like this, will be equal or approximately equal to this thing. So this was the integrand. This was the integrand for k element. And this determinant of j comes in because you are transforming this d area from the actual coordinates to the parent element. So there has to be this j whenever you want to convert a domain from the actual coordinates to the parent domain. So the same thing for f, and after all that, we already know how to do this assembly, and you can enforce your boundary conditions and solve for this equation. So one question arises that we just said that element stiffness matrix can be evaluated with this formula, and the force vectors, the element force vectors, can be evaluated with these formulas. So how many Gauss points should I choose? What is enough and what is necessary? That is the question that we are going to try to answer today. And that is, what is the appropriate order of quadrature required? If I want to integrate this, this is exactly equal to the mapped area. And this mapped area is approximately equal to the numerical values. So for example, if you were to use 2 cross 2, you would take the function value at this point, multiply it with this area, take the function value at this point, multiply it with this area, and so on. That would be your approximate integral. This double integral could be approximately calculated using that. So the question is, should I use 1 cross 1 Gauss quadrature? Should I use 2 cross 2 or 3 cross 3, 4 cross 4, what? How should I decide? How should I decide that how many points do I need to integrate this accurately enough so that I get a correct answer? So it so happens that in this Q4 element, the B matrix, if you take a look at the B matrix, that contains the derivatives of shape functions with respect to C and eta, and actually with respect to X and Y. So let me actually pull up the derivative matrix for B. Um, yeah, so right here, in this case, the B matrix, these are all derivatives of the shape functions with respect to X and with respect to Y. And after we map this element back to the parent coordinates, we say that we can calculate all these B matrices using this Jacobian. So the new B matrix contains all these kinds of terms. The shape function with respect to C. So if my shape function is a bilinear shape function, let's say this is a bilinear shape function in C and eta. So if I take the derivative with respect to C, what would be the order of uh, what would this term be proportional to? So n contains terms like x, y, and xy, right? For Q4 elements. And if you try to express that in terms of Xi and eta, then it contains terms like C, eta, and the product of Xi and eta. So if you take the derivative with respect to Xi, this term will turn out to be linear in eta. If you take the derivative with respect to eta, then this term will turn out to be linear in Xi. And that's why all these B terms, this B term is going to be linear in C and linear in eta. So B transpose DB, assuming that assuming that this D, the elasticity matrix, is constant, this is just going to be the product of these two. So it will be quadratic in both. It will be quadratic in C and it will be quadratic in eta. So using the same sort of logic, what would be the order of this Jacobian? Because this is what we are trying to integrate. And if we can find out what is the order of polynomial that this thing belongs to, then we can construct a Gauss rule that will exactly integrate it. Are you following what's the argument here? So the argument here is that we want to integrate this accurately enough. And so we want to find out what is the order of polynomial in terms of Xi and eta that this thing represents. So the first thing that we want to consider is this. We just said that the order of polynomial for B is linear in C and eta. Therefore, B transpose DB is just a multiplication of itself. So that's going to be quadratic in C and eta both. So we just said that this term will be quadratic in C and quadratic in eta. Now, what would this be? What would be the order of polynomial for the Jacobian? It will be linear because Jacobian has terms like what's that? Yeah. So Jacobian has terms like dxc or dx over dxc, dy over d eta. So this term is nothing but this term right here, which will again be linear in, this term will be linear in eta and this term will be linear in Xi. So the product of those two is going to be linear in Xi and linear in eta. So essentially what we are saying here is that this term is going to be linear in Xi and eta, and so the total integrand will be of what order? Cubic. Because we just said that this thing is quadratic, this thing is linear in both Xi and eta, therefore the integrand will be cubic, which means cube and cube. So what order of Gauss quadrature should I use to calculate my integral exactly in C. Let's forget about eta for now. I have something that depends upon C cube. So what order of Gauss quadrature should I use to integrate it in C cube? 2. So the same thing holds for eta also. Therefore, we need 2 cross 2 Gauss quadrature to do full integration. Okay. Um, full integration is 2 cross 2. Um, so here are a couple of statements, and these are things that we are just stating without proving or anything. But these are very important for you to either understand and remember or prove it to yourself. So the thing is that we just said that we want to calculate this element stiffness matrix accurately enough. But that does not necessarily mean that we have to do full integration. What this means is that what we actually want is that our discretized weak form, this was the discretized weak form that we got after plugging in our finite element approximation. That should approach our continuum weak form. This weak form does not contain any finite element approximation. This was the weak form. How did we get this weak form? Can anybody remind me? So this was the original weak form. When we plug in the finite element approximation, we get this. How did we get this? It's the same thing. You take your strong form, multiply it with a u bar, integrate it, right? So that's the original weak form that we had. If you plug in your finite element approximation into that, you will get this. So what we want actually is that after all our numerical integration, this discretized weak form should approach the continuum weak form as h. H is the size of the element. As this h tends to 0, meaning as we shrink the size of the element, it should approach closer and closer to the exact weak form. And once again, this is a very important condition. It can be shown that this condition right here is satisfied if an element that you construct can reproduce the state of constant stress or constant strain. What that means is, just like in our three-noded triangle, that triangle automatically satisfies this equation because if we calculate the stress anywhere within that triangle, it is a constant strain triangle, constant stress triangle. So this condition is automatically satisfied, which means that if you shrink the element size down, your solution will converge. And you should have seen that if you took a look at your problem 3. As you increase the size of the mesh, your element size becomes smaller and your displacements start to converge. Okay. So this is a very important test of element convergence, meaning that now if you come up with a new element which has 10 nodes, how do you check whether that element is going to converge? So one way to check that is using something called a patch test, and we'll talk about that also a little bit later when we talk about higher order elements. But the most important condition is that any element has to at least satisfy this condition. So if I apply constant stress to an element, it has to be exactly able to reproduce that, even on a computer. So the reason for this, another reason for this condition is that rigid body modes you should be able to capture with your element. So for example, if you have a triangle, if you apply a pure rigid body mode, then it should not detect any stress. Okay, so these are a couple of conditions that we'll again talk about later with when we talk about this patch test. But so I just said that this CST element automatically satisfies, and that is because the derivatives of the shape function in the triangle are constant. But for the Q4 and the higher order elements, what we need to show is essentially that if B matrix is a constant as we go into the limit as h tends to 0. So this B matrix was constant for the CST triangle, if you remember. So what we're saying is for any element, as we refine the mesh, our B matrix should become more and more constant. Um, and that also makes sense that if the element is going to converge, then as the element size becomes smaller, the variation of stress within that element will be more or less constant. So this is the condition that allows you to check and allows you to say that in the limit as h tends to 0, your discretized weak form will approach the continuum weak form. So you can associate this continuum weak form with the exact or the analytical solution, and this as your numerical solution. So keeping in mind that if we can assume that B is constant, how do we integrate it? How do we integrate our weak form accurately enough so that in the limit this converges? So the idea is that since we want our discretized weak form to converge in the limit as h tends to 0, we want this discretized weak form, which is actually nothing but d bar transpose, the virtual displacements transpose, times this is the global stiffness matrix, this is the global displacement vector minus global force vector. There's a bar missing here. That should approach to this. So if we assume that each of our element stiffness matrices, this B matrix is constant, then we can pull this entire thing out. If the B matrix is constant as the element size decreases, then we can pull this out, and all that we would have to integrate is this area. So essentially what we are saying is that if B matrix is constant, we pull it out, and now we need to make sure that if somebody gives you 4 nodes, x1, y1, x2, y2, x3, y4, and so on, if somebody gives you 4 nodes, you have to be able to find its area exactly using whatever quadrature rule that you are. Obviously, if somebody gives you 4 points x 1, 2, 3, 4, you can easily find the area by hand analytically, but that's not what we are saying here. What we are saying is we know that we are going to use Gauss quadrature to do this integral, but we do not need full integration. What we are saying is that we can get away with using a reduced integration rule, because in the limit when this is constant, we will pull this out, and all that our Gauss quadrature rule needs to integrate exactly is this area. So this is a subtle point, but you have to make sure you understand this. Anyway, so if you make sure that you choose a minimum, at least a minimum Gauss quadrature rule that will integrate your area exactly, then your weak form will converge. So essentially, to integrate the area, what we are saying is we are integrating 1, and when we transform this integral from the actual element back to the parent element, this dA turns to j dc d eta. This j is again coming from simple change of variables. Just like in one dimension we had dx, and when we changed that to dc, we had to multiply with j. We have to multiply with the change of length. The same thing is happening here. This change in area or change in domain is measured by this j, and this j is a matrix. So how to integrate this thing exactly using a Gauss quadrature? That's the question. If we can integrate this thing exactly with Gauss quadrature, then we can be sure that our element is going to converge, and we do not need to use full integration. So in this case, for Q4 elements, J, what did we decide just now? J is linear in Xi and eta, right? For Q4 elements, since J is linear in Xi and eta, therefore what order integration would I have to at least use? 1, right? 1, if I use 1 Gauss point, it will integrate any linear function exactly. So if my function, this function is linear in C and linear in eta. So linear in C, linear in eta means that I can integrate this thing exactly with 1 cross 1 Gauss quadrature, which is a huge saving because you would have to do this integration for every element. If your mesh has 1 million elements, and if you were using 2 cross 2 Gauss quadrature, then you would be doing this integration 4 million times. If you use 1 cross 1 Gauss quadrature, your size of the problem or the effort, computational effort that you would be using has come down by 4 times. So instead of using 4 Gauss points, you are using 1 Gauss point and you are still guaranteed convergence. So that's a good thing, but there are obviously some other issues also with reduced integration. So as an aside, let's also take a look at another element that uh, we'll talk about this later also. So this element is a quadratic element in both C and eta. So if you remember the Q4 element, yeah, go ahead. So actually, the size of the element depends upon the type of the problem. If you're trying to capture something like a stress concentration around a crack, no matter how small you go, you cannot capture the 1 upon r singularity. But the idea is that in the limit, you are obviously not going to make your h, the element size, go pretty much down to 0. But you will see, just like in your this bending problem that I gave you, you started out with 10 elements, you went to 40 elements, 160, 640, 2000 something elements, and the change between 640 to 2000 elements was not that much. So it's a little bit of a judgment call when you say that how small an element you need. Hmm. Absolutely. So there are two types of error measures that people ordinarily use. The first type of error measure we've already talked about are called a priori measures, meaning you can estimate what is the order of convergence of your error. And in one dimensions we talked about order h square. For linear elements, the displacement converges quadratically. The same thing happens in 2 and 3 dimensions. If your element is linear, your order of convergence in displacements will be quadratic, and your order of convergence in stresses is going to be linear, same order h to the power p. But there are also posteriori measures. So what that means is after you are done calculating, you can use certain error measures, and we'll talk about that also. You can use certain error measures to characterize in this part of the mesh, my error is greater. So I need to refine this part of my mesh. Okay. So in general, yes, there are lots of procedures where you can check what is the error in your solution. Obviously, it will not be exact because it is just an error estimate, but that will allow you to get closer and closer to the solution you want. And this is an important point. You will see a lot of times people show pretty pictures, as they like to call them, of some finite element solution. It doesn't mean anything. Uh, you have to make sure that you put that result into context. If if I'm getting this solution for 40 elements, what is the solution for 160 elements? What is the solution for 2000 elements? What is the solution for 10 elements? Then you can say that, okay, maybe I'm in the range of a good solution. So so anyway, let's go back to this that we were talking about. So this element, instead of multiplying two linear functions in C and eta, we are multiplying the 3-noded quadrilateral functions. So in this case, our shape function, if you go to any location, is going to be quadratic in C and in eta, right? This is quadratic in C, this is quadratic in eta. We multiply them, you will get this function. And which means that the derivatives of this shape functions are going to be, if you take the derivative with respect to C, those would be c times eta square, and if you take derivative with respect to eta, that would be c eta square. So now B transpose dB would be nothing but take this matrix, multiply it with itself, assuming D is constant, and that would be order cubic. The same thing happens for J. If you remember, J in the Q4 case turned out to be linear, but in this case, these terms would be of this order, because this dx over dc will be of the order of this shape function times c. That's the c times eta square right here. And dy over d eta is going to be of this order, c square times eta. So if you calculate the determinant of this J matrix, that is going to be this multiplied with this minus this multiplied with this. In either case, what you will get is c cube eta cube. So what would be the order of full integration in this case? What would be the order of Gauss quadrature that is required for full integration? If B transpose dB is cubic cubic and J is cubic cubic, so the total order would be 6 in both, right? So since we want to integrate our where is that? We want to integrate B transpose dB times J. So the total order of integral would be, so if I choose 3 points, that would give me 2 times 3, 6, minus 1, 5. That will integrate quintic polynomials exactly, which means I need to go one more, 4. 4 cross 4. If I use 4 cross 4 Gauss points, then I will be integrating this Q9 element up to an order of 2 times 4, 8, minus 1, 7. So any 7th degree polynomial would be integrated exactly. Yes. Okay. So this is, if I multiply these two, I need to integrate a polynomial in C to the power 6. Okay. Similarly, a polynomial in eta to the power 6. Therefore, if I choose a 4 cross 4 Gauss quadrature, that is 4 Gauss points in the C direction, then the order of polynomial the order of polynomial in the C direction is going to be 2 times 4 minus 1. If you have n points, 2n minus 1 is the order of polynomial that you can integrate exactly. So 2 times 4 minus 1 is 7, which means order 7 is integrated exactly, which also means order 6 is integrated exactly. And what about reduced integration? How do I how many Gauss points do I need for reduced integration? So what would I need to integrate exactly for reduced integration? Only the Jacobian I need to integrate exactly, which means cubic I need to integrate exactly, which means 2 cross 2. So another point I just want to mention here is that this Q9 element is not a very common element, because if you consider this middle node, the shape function for this middle node will go to 1 at this node and 0 everywhere else. So does anybody remember what kinds of, this would be a bubble function, right? So we can statically condense that out, and there's a nice procedure to actually consider a Q8 element. And the full integration order for that Q8 element actually reduces to 3 cross 3. But anyway, we'll go over that later also. Yeah, great. 6 to 4? You mean this 6 to this 4? I'm not sure. Okay, so let's go over this again. We want to integrate the product of these terms exactly, right? So this is a 6th order polynomial in C, right? And we said that the Gauss quadrature, if I choose n points, the polynomial order that I can integrate exactly is 2n minus 1. So if I choose 4 points, What is the order of polynomial that I can integrate? 7. That means that I can also integrate 6th order, this polynomial, right? So that's how I get 4 cross 4. And for the 2 cross 2, we are just integrating this. We are not worried about this. Okay? All right. Any other questions? Okay. All right. So let's talk about post computation now. Let's say we have used our numerical integration. We have used our Gauss quadrature, either full integration or reduced integration, and we have formulated all our element stiffness matrices. We have assembled them, and we have solved solved this global equation using boundary conditions. So all that we know how to do. Um, so this post computation is the first thing that we try to do is we actually try to plot displacements, and this is something that you've already done. You take your global displacement vector, pull out the degrees of freedom that are corresponding to, let's say, an element that you want. So in this case, if I go to element 1, it has corresponding degrees of freedom 1, 1, 2, 3, 4, 9, 10, 7, 8. So we need to pull out those specific degrees of freedom from this global displacement vector, and we can straight away plot that. So there's not a whole lot of new concepts in this, but you can just take a note that this type of procedure is called restriction. So what we are saying is we take our global displacement vector, we pull out those certain degrees of freedom, that is called restriction. This is sort of the reverse of assembly. In assembly, what we do is we take our element stiffness matrix and we assemble it into a global stiffness matrix. So plotting displacements is not that big a deal, but plotting stresses is, and especially for Q4 and higher order elements. So if you remember from the triangle code, this was the line that we were using to calculate our stresses after our solution was obtained. So, and in the code LM post, I was missing this D matrix. How many of you did not notice that? Okay, so hopefully, okay. But yeah, we are not going to penalize you for that. But if you can, just make this correction. And so anyway, in CST, in the triangle, this thing turned out to be constant for the entire triangle, meaning go any point anywhere, your stress within the triangle is constant. But for the Q4 element, this B matrix is not constant, which means that the stress within the element is not constant. And we need to find out how we are going to plot all these stresses. So so in order to plot all these stresses, let's say we pulled out the element degrees of freedom. Again, going back to element 1, we have these element degrees of freedom 1, 2, 3, 4, 9, 10, 7, 8. We pulled those out and we constructed this matrix at a given point. So for example, if we were using 2 cross 2 Gauss quadrature, we constructed that B matrix at this point, this point, this point, and this point. And that B matrix at all those 4 points is going to be different. So if you want to calculate the stresses now, you can calculate the stresses using those B matrices at those 4 points, but you would have to construct that B matrix all over again, and that can be quite expensive. So one way to get around that, and when you code up this Q4 element, that would be the next homework. You will need to calculate all these stresses again, and so we'll talk about how you can either store these matrices or construct them again, depending upon how you go. Your code might run faster or slower, or take up more memory, or and so on. So So the alternative to using this 2 cross 2 Gauss quadrature is just like we talked about, we can use reduced integration, 1 cross 1, meaning we go to the center of the element, we calculate our B matrix there, we calculate this B matrix at that point, and that is not that much of an expense. If we are calculating one B matrix per element, we can calculate that quickly, multiply it with the D vector, and we will have the stresses. Yes, we'll talk about that next. So what are the consequences of using this reduced integration? So if we use this 1 cross 1 Gauss quadrature, is that accurate enough? We know that it will converge in the limit, but if we use big elements, is that accurate enough for big elements? So essentially, if we use 1 cross 1 Gauss quadrature, we are saying that our k element is approximately equal to this quantity. If you remember, there was a summation over I and j for Ci and Cj. In the previous pages, if you remember, this was there was a summation over the number of Gauss points. But since in this case there is only one Gauss point, we don't need to sum it over anything. We just calculate this B matrix at this point. D matrix we have assumed is constant. This B matrix again is the same matrix at this point, Jacobian at this point, and then we take this product and multiply it with 4. This is a multiply sign. This 4 comes from the fact that the weight function for the zero Gauss quadrature is 2 in Xi and 2 in eta. So 2 multiplied with 2 is 4 here. So essentially we said that the integral for our k element, instead of having to do any integrals, all we are going to do is calculate the value at this point, multiply it with 4, and that's our k element. And that is obviously a big approximation, but let's see how that affects our results. So one thing I've already said is that it requires much less computation, so it will be much faster. So that's a good thing, meaning that's the upside of this. Another upside of using reduced integration is something called superconvergence. Superconvergence of stress. And what that means is that people actually tried over many years to code these types of elements with different types of quadratures. And they found that if you actually calculate your stresses, instead of calculating it at the 2 cross 2 Gauss points, if you calculate it at one order less, if you calculate it at one order less than what is required for full integration. So if you remember, for the Q4 element, the full integration was 2 cross 2. And if you calculate at one order less, that would be 1 cross 1, we get an optimal convergence in terms of stresses. And what that means, again, in terms of our error measures that we were just talking about, error in displacement is of the order of HP plus 1. Do you remember that from one dimension? We said order of error in displacement is HP plus 1. Therefore, order of stresses is H to the power P. But if you use these optimal locations, which are called Barlow points, which are one order less than the full integration, in this case that's the 1 cross 1, your order of convergence of stresses also goes up. It is actually of the order of HP plus 1, the same order as your displacement. So this phenomena is, again, it is people have written papers about this and have proved this this fact, and you can also observe this in your codes. So the idea is that for a Q4 element, full integration is 2 cross 2. One order less than full integration would be 1 cross 1. If you calculate your stresses here, you will get superconvergence of stresses. So that's also a good thing. So we have an upside here, which also brings us to another issue. This issue is about how do we do the stress averaging for Q4 and higher order elements. So if you remember, for the T3 element that you are working on right now, we just said that the stress or strain is constant within the element, which means that if I have one element here, another element next to it, and actually I think I have a picture of that too somewhere on this last page. If you see, this was the solution that we got from the 10 element triangle problem. The stress within each triangle is constant, right? Which means that, let's say if this value is what, 0.4 or whatever this is, that's somewhere up here. We have a constant, we have a constant stress right next to it. Another stress here, another stress here. So if you consider this edge, there is a discontinuity of stresses at the edge, okay? And that also exhibits this, we see that same sort of discontinuity in Q4. So consider this mesh. At the bottom right here, I have 4 quadrilaterals, okay? These are 4 quadrilaterals at the bottom, and let's say I've done my computations, I have found out my solution, and now I'm calculating or trying to plot my stresses. So if you were to calculate your stresses with this formula and plot them exactly everywhere over the entire element, you would see that at the edges of the element, you would have discontinuities in stresses, okay? And what that also means is, from this picture, it is hopefully clear that the stress in the element at the nodes, meaning if this is your mesh, if you calculate your stress using this formula at the nodes, it is much more worse than the actual value of stress. So the value of the stress at the nodes using this formula is much worse. So instead, what we do is we calculate the value of these stresses at the Barlow point, and then we project that value. Let's say we are trying to calculate or do stress averaging for this point. In the triangle case, it was not a problem. You take all the neighboring elements, sum them up, divide by the number of elements that are there, and you have your average stress at the node, okay? In Q4, you do the similar thing, but instead of going for instead of averaging these 2 cross 2 stresses, you calculate your stress at the Barlow point and take the average of that at this node. So this is how you would do stress averaging for a Q4 element. On the other hand, if you are using full integration, then you would somehow have to average these 4 values at this node, these 4 values at this node, and these 4. So you would have a total of 16 values at this node. And sometimes people use a weighted average, meaning that the Gauss points that are actually closer to the node get more weight, the Gauss points which are farther away get less weight, that type of stress averaging. But this is more or less a sort of an ad hoc procedure to try to come up with a stress at the node. Because if you look at it, your solution has already been computed. Your D global you have already obtained. After you've obtained your D global, everything else is post computation. So it doesn't matter how you want to interpret the solution that you got from your finite element. You can interpret it in any way you want. So people use different types of stress averaging procedures just to get the value of the stress at the node, and that in general should be smoother than this. And we've seen that hopefully in your code for the triangular problem, the same sort of thing happens. The amount of discontinuity, you mean? Yeah. Not necessarily. So there could be, that amount of discontinuity could be problem dependent. If you have some sort of a singularity, or if your element is closer to a crack edge or something, you might get huge discontinuity. So, but anyway, so yeah, you would have to find some sort of an average to calculate stresses at nodes. Then you can plot your average stresses. Okay. All right. So let's talk about a couple more consequences of this. So one consequence is that if you use reduced integration, your mesh or your problem actually becomes a little softer. And what does that mean? Um, so here I'm making a statement which is also something that you need to understand. A finite element solution is usually stiffer than the actual continuum problem. And this is something that we saw in the one-dimensional problem also. If you have your one-dimensional problem, if you apply a body force throughout the length, and if you try to calculate the exact solution, you will see that the exact solution, black curve, is always above your finite element solution. So essentially what we are saying in finite elements is that I am not going to allow any other mode of deformation other than linear. If this is a finite element in one dimension and I have a bar, I'm saying that this finite element can deform only linearly. So I'm making it a little more stiff than it might actually be, right? So that's the that's the logic that we are saying here, that a finite element solution is usually stiffer than the actual continuum problem. We don't know anything about the real world problem. The continuum problem is the mathematical model that we have. In this case, this is the same sort of logic is valid for a two-dimensional or three-dimensional problem. In this case, we are saying that we will take parts of our domain and we will assume that our solution varies linearly within that element. So again, we are constraining, we are saying that this element cannot deform in any other way other than linear. And if we say that, then our domain becomes much more stiff. And you can see that this phenomena actually happens so much that the actual displacement that you got from your 10 element problem was so much smaller than the actual full displacement with the 2000 element mesh. And that another term for this kind of a phenomena is called locking, but we'll talk about that next time. So the idea is that finite element mesh will in general be stiffer. If you use full integration, then you're not helping. Okay, so that if you use full integration, meaning you have found out your element stiffness matrix exactly, then you've not helped your problem in becoming softer. But it so happens that if you use reduced integration, you allow your element to be integrated a little more inaccurately, and that allows some more flexibility in your element. So the two effects sort of cancel out. On one hand, we are saying that our displacement cannot vary anything other than linear. And on the other hand, we are saying that, okay, to compensate for that, we are going to use a reduced order integration that will allow some more flexibility. So the two effects cancel out, and actually you get a much better solution. So the softer, more accurate response that you get with reduced integration is a plus again. Okay, but a big minus or big downside of using reduced integration is that there can be mesh instabilities. Obviously, now that you are approximately calculating your element stiffness matrix, you've made your element softer, which also means that sometimes it can become unstable. And let's take a look at that. So if you remember our K element for the Q4 element, it was going to be 8 cross 8, right? So that means that it will have 8 eigenvalues and 8 eigenvectors. How many of those eigenvalues are going to be 0? So what do 0 eigenvalues mean physically? They are rigid body modes, pure translation, pure rotation. Okay, so if you get 8 eigenvalues, you will get corresponding 8 eigenvectors, which will be nothing but the shape of your deformation. So if you start with a square element, and if you take that element and shift it up vertically like this is a pure translational mode. Okay, this pure translational mode corresponds to a 0 eigenvalue, and this is the same idea that we talked about in the one-dimensional problem. So this is a one-dimensional element. We found that if you find the eigenvalues of this element, one eigenvalue was 0, the other eigenvalue was 2. So that means that the pure deformational mode is linear for this element. and the only rigid body mode in one dimension was translation in one dimension. So for the midterm question that I asked you, if you assemble this into a truss element in 2 dimensions and 3 dimensions, um, if I assemble a truss element in 2 dimensions, you would get a 4 cross 4, out of which 3 eigenvalues would be 0. And if I assemble that truss into a bigger space truss, then I just have to try to find out how many rigid body modes does this have, or how many mechanisms does this truss have. That would be the number of 0 eigenvalues. So 0 eigenvalues denote rigid body modes once again. So in this case, this is a vertical translational mode, this is a horizontal translational mode, this is a rotational, pure rotational mode. These are the only 3 rigid body modes in 2 dimensions, right? You can, in 2 dimensions, you can have x displacement, y displacement, and rotation. Those are your 3 rigid body modes, meaning 3 eigenvalues will be 0. Okay? And the other ones are all deformational. So in this case, if you calculate the eigenvalue and the eigenvectors corresponding to these 5 modes, they will not, the eigenvalues won't be 0. They will be positive, because you need positive energy to deform the element into these modes. So we just said that full integration is too stiff, but with reduced integration, sometimes it can become too soft and unstable. And the 2 particular modes that this reduced integration introduces are this and this. So if you take a look at this, we said that reduced integration, we are going to calculate our value at this point, value at this point. So if I have my square and it deforms into this kind of a trapezoid, if I measure my Jacobian at this location, it will be 1, because Jacobian is nothing but the area of the deformed shape. And you can see that the area of the original shape, area of the deformed shape, exactly the same. So Jacobian turns out to be 1, which means that if you use reduced integration treats this also as a rigid body mode, as a 0 energy mode. It does not take any energy for that element to deform like this if you use reduced integration. Similarly for this, if I calculate the Jacobian at the middle of the element for this type of a deformation, the J is 1. So it says that if I calculate the integrand, it says that I have not deformed. So these 2 become the 0 energy modes, or they are also sometimes called hourglass modes. And that term is right here, hourglass modes. And the reason that they are called hourglass modes is because this kind of looks like an hourglass, right? And for small meshes like this, if you use a 1x1 Gauss integration, then without applying much load, your mesh will deform in these different types of modes that are called 0 energy modes or hourglass modes. So this is a mesh instability of a problem of reduced integration. So anyway, we'll continue on Monday. All right.